What's up, guys? Dylan Coates, and welcome to day 13 of Advent of Code 2020. So before we get into it, just a reminder that a link to all my code is down in the description below for GitHub, and let's get into it. So, alright, day 13, shuttle search. We made it safely, but we're going to have to take a shuttle to the nearest airport. Bus schedules are defined based on timestamp and number of minutes. So the bus's ID number, it departs every multiple of its ID number. And the first line is your estimate of the earliest timestamp we could depart. The second line is the bus IDs, and X means the bus is out of service. And so the earliest bus, your goal is to figure out the earliest bus we could take to the airport. The earliest bus is 59. It doesn't depart until 9:44, so we would need to wait some time. What is the ID of the earliest bus multiplied by the number of minutes we'll need to wait for that bus? Okay, I don't think this should be too bad. Let's go ahead and paste that in our input, just 2 lines today. So let's get into it. So we'll say with open file, nope, input 13.txt as a file. And today we'll say data is equal to file.readLines. Data is equal to file dot line dot strip for line in data. And then you can see here that we have all these commas, so let's go ahead and split this up. So we're going to say data or data 1 is going to be data is equal to data1 dot split, and split it by the commas. So now if we go ahead and print data, let's go ahead and see what that gives us. What's going on? Okay, this should be data 1. Okay, so now you can see it's broken up into lists. All right, let's go ahead and write our first function. So let's def get ID and minutes, because why not? And we'll start off by saying here our arrival time is going to be equal to data int data 0, and then IDs, the bus IDs will be equal to data 1. Now we'll say for ID in, well, we also have to deal with X's, so we'll say for item in IDs, if item not equal to X, not equal to X, then ID is going to be equal to int item. Else continue, because we don't need to do anything if it's an X, we'll just ignore it. So then we can say, well, we're going to be searching for the lowest wait time, so we'll say lowest, and well, we need to make this a really big number to start. And so then we'll say, because then we can say if, well, we need to say basically, so say that our wait time is 100, we need to get the first multiple of the ID after 100. So we'll say I don't know what we could say, ID ID multiple is going to be equal to our arrival time divided by 100? No, divided by our ID. So this will give us the times that our ID will go into arrival, and then we will say that that our difference is going to be equal to ID times ID multiple plus 1, because so if we just multiply ID by ID multiple, then that'll give us a number lower than arrival. But if we do the next multiple, then that'll be the first multiple of ID above our arrival time. And then we'll say minus arrival. So the difference between the first multiple of ID and arrival time. And then we'll say if difference is less than lowest, then lowest, of course, will be equal to difference. And then we also need to keep track of low ID. So the ID, of the lowest number. So low ID is going to be equal to our current ID, and then at the end return low ID times lowest. I think that'll give us the answer. So let's go ahead and print get ID minutes, and if we go ahead and run that, 1:15. Let's try it. All right, so there we go for part 1. So now continuing on to part 2. The shuttle company is running a contest for anyone that finds the earliest timestamp such that the first bus ID departs at that time, and each subsequent listed bus ID departs at that subsequent time. And the first line of our input is no longer relevant. So for example, if we have this example, bus 7 departs at time t, which is a multiple of 7. ID departs at t plus 1. 59 departs at t plus 4. Okay, and that makes sense because we skipped 2 and 3. 31 departs at t plus 6. Okay, so I think what we have here for part 2, and we're just going to be finding that time. Where they all kind of happen in a row. So yeah, you can see here, they all kind of happen in a row. But then they say, however, with so many bus IDs, it'll be larger than whatever this number is. So they don't want us to use brute force. So we can say here, say we have bus, so we have a list of, so we have n buses, and bus k at index I departs at a time t. And so I guess this is true for the first bus, and then at time t plus I. So that means that we have t plus I mod k, because t plus I needs to be a multiple of k. So for example, this number is a multiple of 13. This number would be a multiple of 59, and so on. So because this ID represents our k value, because it's bus k. So I don't know how that helps us yet, but we know that that's going to be equal to 0. Now, I believe that there is something called the Chinese Remainder Theorem. If we look it up here, The Chinese Remainder Theorem, learned about this in computer science, allows you to solve a set of problems, I believe. Yes, okay, so if we have some, in our case, some t and I, mod k, if we replace for different, so we have t stays the same, and then different indexes mod some different bus ID for some for a whole set here like we have. So basically what this allows us to say is we say n is the product of all of the n sub i's, so that would be n is the product of all the bus IDs, and then so if we have the same time different indexes mod different bus IDs, then we can solve this system for I guess you could call these like constraints, so or congruences. So we can solve the system. So is that solution in here? Yes. Okay. So the solution, and I think this is the time that we're looking for, is going to be equal to the bus index. And what do we get here? So n sub I is going to be equal to the product of all the bus IDs divided by a particular bus ID. And I'm guessing m sub I is the modular inverse mod the bus ID. And the modular inverse basically is this partial product here. So this partial product times the mod inverse of itself, or mod, and then mod bus ID is going to be equal to 1. And so this is probably really confusing, but we're going to do our best to get to write it into code. So I guess we can say here, doing some modular arithmetic, so t mod k is going to be equal to -I. And so that also means that t mod k is equal to k minus I, because t mod k gives the difference between t and k, because it's a remainder. So this I is basically the distance between t and a multiple of k. And so in order for that to help us, I guess we can say, well, we want to, so k minus I, well, we want this whole thing to be mod k, because we want it to be between 0 and k, because our answer is going to be between 0 and n is the product. So we want it to be mod k, and then this I also mod k, because now this is kind of like really complicated to explain, and I don't understand it too well, but I think this is how it works, because we want to keep it between 0 and k. Especially because if we have k minus I, we can end up with a negative value, and we want it to be between 0 and k. So let's just see what we can do with this to start. So we'll say def get earliest time, and then I guess we'll read in, so IDs is equal to data 1 but we're going to be checking, I want to make this an empty list, because now we're going to be checking Okay, so for I in range data length 1, we'll say item, because we need to know the index of the number that we're looking at, because that would be our A sub k. So item is data 1 I if item not equal to x, then k is equal to num or int item. So k is our bus ID, and then let's go ahead and say, well, we want to keep I in between 0 and k. So we'll say I is equal to I mod k. And then that also goes right there. And then, so then we can say IDs.append, and we're going to give it a tuple. And the first value will be the I mod k. So give it I, and then, well, we want to give it k minus I mod k, because that's basically right here. And so this will correspond to an index mod k, and then yeah, because it's this index here, and then we'll give it k. This might not make too much sense yet, but hopefully we'll be able to see where this is going. I kind of have an idea in my head. So we add all those in, and now we need to check we basically need to compute this and add it to a total. So total is equal to 0. So we're going to compute this for every k and a sub I. So this represents a sub I, and this represents just a bus ID. So, well, we also need to know n, which is the total product. So, so we have a full product is equal to 1, and then we'll say full product times equals to k. And then so we'll say for ik in IDs well, let's just go ahead and see what's in IDs for now. So IDs get earliest time. Let's go ahead and run that, see what we get. Okay, so as you can see, all the IDs are less than the k value. And the reason why this is say all the way over here we have index 29, or we have k 29, but what if this is index 5? We want, or what if this is like index 50, but we want the index to be between 0 and 29. So that's why we had to, so that's why we did this with the mod k, because we want the index value to be in between 0 and k, since that's kind of what's going on with this Chinese Remainder Theorem. Okay, so print IDs is good. And then for ik and IDs, well, partial product is going to be equal to full product divided by k. Okay, so partial product is n sub I. A sub I is going to be equal to this I value here, and we need a mod inverse. So let's write a function def mod inverse, and I've definitely learned how to do this before, and I do not remember, so we're gonna look it up. Let's see, mod inverse. Let's try this one. Maybe it'll give it to us in Python. Okay, well I can explain this. So given some, I know what mod inverse gives us is find some x such that a times x mod sum n is equal to 1. And so if we pass in an a and an n, then a mod n, so there exists some x, so that if you multiply a and x and modulo it by 1, then and modulo it by n, then you get 1. So for example, if you have, I don't know, like three, if you have, for example, like 3 times x modulo 4, we're trying to find some x so that if we multiply 3 and x and mod it by 4, then the answer is 1. Now that x would equal to 11. X is equal to 11 because 3 times 11, man, I keep forgetting comments. 3 times 11 is equal to 33, and 33 mod 4 is equal to 1. And I mean, if we try that down here at the bottom, 33 mod 4 is equal to 1. So basically, for any a and any mod, so this would be n and this would be a, search for the x so that we can satisfy this equation. And the way that we do that here, according to this beautiful website, is so a is equal to a mod m, because to start off, we want to put a between 0 and our modulo, and then just for every x from 1 to m, if this is true, like I just showed here, then return x and return 1 otherwise, and that would only hit if it's mod 1. So we could say a is equal to a mod n, and for x in range 1 to n, if a times x mod n is equal to 1, return x. And in the case that if n is equal to 1, return 1. Okay, so hopefully that works, and we will test that it works. So inverse is going to be equal to mod inverse, and what would our a value be? Well, we've been modding everything by k, so I'm guessing k is our mod. And partial product, let's see what this says here. So yeah, so this is basically, so this m sub I is our is going to be the modular inverse of partial product, and this is from the extended Euclidean algorithm. So I'll provide links to these pages down in the description so you guys can check them out too. So then this will be partial product, and then we'll assert that inverse times partial product, just to make sure that mod inverse is working, because if that's the problem, then I guess we'll have to fix it. And assert that's equal to 1. So let's hope that we never see that. And then, so this this term for some particular I is going to be equal to inverse times partial product times I, and total plus equals term, because it's a summation. And return total. And remember, our answer should be between, you know, I thought it said something here. Oh yeah, there's only one integer x such that x is between 0 and our full product. So mod full product. Oops. Mod full product. And I messed that up again. Okay, return that. So now, God, this was a lot of number theory. I hope it works. And I know it's pretty confusing, and I'll try and explain it again at the end once we get it right. So let's go ahead and exit and run our code. Okay, and okay, we forgot to mod this, so we're gonna mod it by k. Okay. Let's try that. Oh, okay. And there's the answer. So real quick, I'm going to try and explain what's going on here once again. So basically, so to recap, we have a type of problem here, the Chinese Remainder Theorem, where we have some x's, which is a time that we're leaving, and sub I, an index of the ID in the list, mod the ID. And so in a system of congruences like this, then if, say, we have some number capital N, some number N, that is the product of all the bus IDs, then there exists one X such that it satisfies our constraints. Which are described like this. So there's only one X that satisfies some constraints where they appear all in a row like this. And we can find that X by summing up the index mod K, the product, the total product divided by the particular ID we're looking at, and then the inverse, the modular inverse for that particular partial product. So if we sum all of those up, then we get our unique X mod K. And you can see that here. So we have time plus an index in the list mod K. And so this is index is equal to that. So this is index mod K. And I explain that because, say, for example, if this 37 comes at index 50, if the index is greater than the bus ID, well, we want to mod it by 37 so that the index is now between 0 and 37. And so we add that to the list along with the bus ID, and we calculate our full product just by multiplying all the IDs together. And then so our partial product and sub I is equal to the full product divided by our ID. Then we find the modular inverse, and then we already have the index mod k. So just multiply those all together and then add it to the total sum and return that mod the total product because it's between 0 and n, and that's our answer. So if you found this solution helpful, albeit probably a little confusing, drop a like down below. I'll try and answer any questions you have, and I'll see you back here tomorrow for day 14 of Advent of Code. Subscribe for more.